So in this video, we're going to talk about stretches and compressions, both vertically and horizontally. So we already saw that if you multiply a function by -1, or if you multiply the input of the function by -1, it will reflect the graph, right? Either over the y-axis or the x-axis. So what if we multiply the function by a different number, say like 2 or maybe 1/2? So I want to look at two different graphs here. First, let's look at f of x equals 2x squared. And then on the right side here, we'll call it g of x equals 1/2 x squared. Okay. And we want to think about the points for both of these functions. Okay. Let me keep this consistent. So if we think about our typical points that we've been using for this graph, right, for the x squared graph, namely 0, 1, -2, or sorry, 0, 1, 2, -1, -2, then let's just think about what the output would be of this function when we plug in these numbers. Okay, so we plug in 0, we're still going to get out 0. We plug in 1, we're going to get 1 squared, which is 1, times 2, which is 2. When we plug in 2, we're going to get 2 times 4, which is 8. So compared to the parent graph, right, the parent graph had the point 0, 0, 1, 1, and 2, 4. So these ones are being stretched vertically, right? That point that was at 1, 1 is now being stretched up to 1, 2. The point that was at 2, 8 is being stretched up to 2, 4. And then same with the points on the other side, of course. The graph will still be symmetric, so nothing's going to change there. Now, if we think about what happens on the 1/2 x squared, if the 2x squared points, if that's like a vertical stretch, we then might expect this to be a vertical compression. Okay, so if 0, 0 is just going to stay the same, this point's not being altered. If we plug in 1, we're going to have 1 squared, which is 1, and then times 1/2. So we're going to have 1/2, right? So basically all the outputs of the parent graph are being multiplied by 1/2, in other words, divided by 2, right? So 2, 4 is going to be then 2, 2. And then same with these 2 points, since it is going to be symmetric still. So on the 2x squared, the outputs are being multiplied by 2. And on the 1/2 x squared, the outputs are being multiplied by 1/2. So again, this should make sense if we just think about like this, f of x equals x squared as the parent graph, then this one up here would be 2 times f of x, right? I gave it the same name, but same idea here. Okay, so we're taking all of the outputs, all of the f of x's, and we're multiplying them by 2. Okay, so let's go ahead and just put these graphs on here real quick. Okay, so again, just a quick sketch of these. Won't be perfect, but we can just look at what these will look like. Of course, this one is going to be, it's going to be, it's because it's being stretched vertically. That 2, 8 is already a pretty far away point based on the scale that we normally use. So we'll just kind of imagine that one. So it's going to look something like this. Okay. So it's like you took that original graph and then you stretch it up, right? The original graph would look something more like we have a point at 1, 1. We have a point at 2, 4. I'm sorry, 1, 2, 3, 4. So right here. right? So that graph looks more like this. So this one's being stretched upwards, right? It's like we're pulling that graph and then we're stretching it up. So it's getting larger faster. And then on the other side here, the 1/2 x squared. Okay, so we have 0, 0, 1, 1/2, and then 2, 2. And then it's symmetric on the other side. So that's going to look more like this. Whereas again, that parent graph, the x squared, I'll put that in red here. Okay, so we have 2, 4, negative 2, 4. So that looks more like this. So we call this a compression. It's like we're pulling the graph down, right? We're pulling all the points downwards. So in general, the idea is with the parent graph, this coefficient in front of this is just 1, right? So we typically will call this number A, the number that is in front of the leading coefficient. In other words, that is the leading coefficient. In other words, the coefficient in front of the variable with the highest power. In this case, we just have the one variable power with a power, right, which is x squared. But if we have like x squared plus 2x plus 3 or something like that, the x squared part we would call the variable with the highest power. So then its coefficient we would call the leading coefficient. So we like to use the letter A for the leading coefficient. So in general, if g of x is equal to a times f of x, then if let's say case 1, if a is greater than 1, the graph will be stretched, okay, vertically. If a is between 0 and 1, so like the 1/2 example, the graph will be compressed, again vertically. And then if a is less than 0, then there's going to be a combination of this with a reflection, right? Because the negative will reflect the graph, and then the number will stretch or compress it based on these rules. So we can just think of these two cases, and then if it's negative, we would combine it with whichever case is appropriate there. Okay, so this is a vertical stretch or compression. Now in terms of where this would fall in terms of like the order of transformations, this again is a multiplication step. So it's going to fall in the same category of as the reflections, right? We do them all at the same time because they're all just multiplication. So now we will look at the horizontal version of this, which is essentially the same thing, but we are going to be multiplying some number by the input, by the x, right? So this would be something like, we can write down the rules first because they're going to follow essentially the same rules. So if g of x equals f of b times x, okay, so now the b, we're using b this time for the constant that we are stretching by or compressing by. And if it's inside that parentheses, if it's being multiplied by the inputs. Now, as you might expect, the rules are going to be backwards with the horizontal, just like we saw with these shifts. Okay. Then if b is greater than 1, then the graph will be compressed by 1 over b. Okay, so it's different in two ways here. First of all, it's different because the compression and the stretching are backwards from the vertical version. Okay. And second, we're not doing it by b, we're doing it by 1 over b. So then if b is between 0 and 1, so 0 is less than b is less than 1, then the graph will be stretched by, again, 1 over b. Okay. And we should specify for both of these that we mean horizontally. Right. Okay. So let's take a look at an example so we can see exactly what we mean by this. So again, we'll use our trusty x squared graph. We'll look at 2x squared, and we will look at 1/2 x squared. So first of all, one thing that we might notice right away is that in this instance, because of the way this function works, if we were to simplify this, like if we did 2x squared, we would get 4x squared. So we can see that a horizontal compression, this would be by the 2 term here, is going to correspond to a vertical stretch of 4. Okay, and then same thing on the 1/2 case, that's going to be 1/4 x squared. So that's going to be like a vertical compression by 1/4. So let's just go ahead and look at what some points would be here. So if we put in our trusty points, if we put in 0, we're still going to get out 0 because everything's being multiplied by 0 here. If we put in 1, we're going to get out 4. Okay, because 2 times 1 is 2, squared is 4. If we put in 2, we're going to get out 8. If we put in -1, we're going to get out 4. And if we put in -2, we're going to get out 8. Okay, so we're keeping that symmetry around 0 still. But the points are pretty different here. They're, I mean, you can think of this would be exactly what would happen if we did a vertical stretch by 4, right? And actually thinking of it like that, I'm realizing this should be 16, right? 4 squared is indeed 16, not 8. But regardless, we can see what that looks like on the graph now. So we're thinking of it in terms of the horizontal now, like if we're pulling the graph out horizontally or pushing it in horizontally. So we have our 0, 0, 1, 4, -1, 4, and then 2 is really high up there, 2, 16, -2, 16. Again, for reference, let's go ahead and make our original graph, the parent graph x squared. Okay. So we can see that compression, right? It's being pushed in, right? The points are being pushed like towards the y-axis, the x values. Okay, so that's what we mean here. Now let's go ahead and look at it on the green side, the 1/2 x squared. So again, just like I've kind of mentioned in the other videos, I think it's best just to work off of like a set of points, no matter what the graph you're doing is. Like pick like 5 points that give you a good general shape of the graph and just apply the transformations to those points. And then that'll kind of give you a feel for, what the graph should look like. You can kind of like do the transformation steps in your head, but you don't have to write every single step out one by one, right? Unless it helps, and if it does, then by all means do it. And on the first few, it's probably a good idea to do that. So anyway, so now we're going to plug in 1 and get out 1/4, right? 1/2 squared is 1/4. We're going to plug in 2, we'll get out 1. 2 times 1/2 is 1. 1 squared is 1. And then we're going to keep that symmetry again. So these are going to be the same thing. So this one, we're going to take a look at what this looks like. So we're going to have 1 1/4. That's going to be really close to the x-axis. Same with -1 1/4. We're going to have 2 1 and -2 1. Okay, so this is a really wide graph. So it's being stretched horizontally by 1/b, which would be 2 here, right? So we go ahead just to look at those parent graph for reference again. Okay, so we can see exactly what's going on here. So we can see that horizontally speaking, the graph is being stretched outwards. Okay, so it's going to end up with a graph that looks like it's wider than that original graph. And here we've just been using x squared as the example for all of these. Every type of graph is going to have its own way that it's affected by these kind of transformations. But this is a good one, I think, to kind of showcase these changes. So again, just when you're doing these on your own, when you have multiple transformations, you can do each one in steps, and it's good to see exactly what each transformation is doing to the graph. These are all of them now, right? We've gone through all of them. So we have the shifts, or sometimes we call them translations. We have the reflections, and we have the stretches and compressions. Okay, so you can kind of, so you can do them all in steps. You can just apply the changes to the points, just being mindful of the order. You can kind of go through the steps of each individual graph in your head and just kind of put what the final graph would look like on the paper, right? Doing that in combination with the points, like altering the points themselves, I think is probably the best idea in terms of like efficiency and in terms of, accuracy, making sure that you have the correct graph.